Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're just going to do an application involving the tangent function, and it's titled an application because there's not a lot of applications that involve the tangent function. It is true that a lot of applications use the tangent function, but not very many of them actually are based solely on the tangent function. And this one right here is the most common application given when you're dealing with a tangent function. So we might as well just do it, right? So let's read this out. A lighthouse is 100 feet from a long straight wall on a beach. The light in the lighthouse rotates through one complete revolution once every 4 seconds. Find an equation that gives a distance d in terms of time t and graph this equation. Now, that last little sentence, or 2 sentences there, find an equation that gives a distance d in terms of time t, is based upon a picture I haven't given you. So let me give you a picture. So the picture goes like this. You have some wall along a shoreline. So this will be our wall right here. There's our wall. Okay, and then you have a lighthouse somewhere out in the ocean. So I'm just going to draw a little island, and then you have some type of lighthouse here, and it's emanating a light. So it's all glowy and stuff. And we know that the lighthouse is 100 feet away from this shoreline. So let's go ahead and maybe put a different color for that. And say that this distance right here is 100 feet. So I'm just, looks like I've created an egg, 100 feet. All right. And what I mean by D is that you have the light beam going out, hitting this and keeps moving, right? It keeps hitting along the wall, the beam of light. I want to know D. I want to know what that distance is as a function of time. That distance being the distance between the nearest point on the wall to the lighthouse. So this point right here to where the light currently is. I want to know what that distance is at any given moment using a function, specifically, as they said, a tangent function. So one thing that you should note here is that this is a right triangle. Right here is a right triangle. And here's that angle theta that they also mentioned. And we know that the angle theta and the side d and the side 100 are all related by a trig function, specifically by the tangent function. So we know that the tangent of that angle is going to be d over 100. Okay. The problem with this is that this angle is given in radians. That's not actually a problem, but they don't want the distance in terms of an angle. They want distance in terms of time. Well, we know that it does a full rotation all the way around 360 degrees or 2 pi radians every 4 seconds. So every 4 seconds it goes through a full spin. So this goes all the way around every 4 seconds. So let's see if I can trade out this theta here. Let me use my black ink. There we go. And let's trade it out for something a little bit better. So tangent of, well, I would like to trade theta out for something involving time. It goes through 2 pi radians every 4 seconds. Now remember, radians is a unitless measure. And so I don't want to write 2 pi over 4 here, because then if I do, I'll have over seconds, right? I need to cancel out that word seconds. So to cancel out the word seconds, this is just a unitless measure up top, but to cancel out the word seconds, I'm going to multiply by time in terms of seconds so that the seconds will cancel. Time in terms of seconds. And again, the seconds will cancel, and we are back to having a unitless measure, which is radians. And so tangent of 2 pi over 4 is pi over 2. Pi over 2t is equal to d over 100. That is our equation that relates how long it's been to the distance the light has covered across the wall. And of course, we can graph the equation d. So let's graph. This implies d is equal to 100 tangent of pi over 2t. We could graph that by hand, although I got to tell you, it won't look like anything special, but we could totally graph that by hand. If you want to graph it by hand, you have to note there is no amplitude for a tangent function. There is a period here. The period is not 2 pi over b, but pi over b because it's a tangent. It's pi over 2, which is 2. And what does that mean? It means it takes 2 seconds for the other beam to hit the wall, because the beam doesn't go one way. The actual beam goes both ways. So I know it takes 4 seconds for this side of the beam right here to come back, but there's another side that's going to come back around and hit it. So it only takes 2 seconds for the cycle to actually continue. So it's just a little important point to be made. So the period is 2. And remember, with the tangent and cotangent, the step size is divide the period over 2. So step size is equal to period over 2, which is just going to be 1. And let's see, anything else I need there? We don't have a phase shift. We don't have a vertical shift. So phase shift and vertical shift are both 0. So to graph this, I will just draw in here an x-axis, a t-axis technically, because time. It's a regular old tangent starting at time 0, and it increases up just like that. There's a vertical asymptote in here. Notice I'm freehanding this rather than using my ruler. And remember, we start, because there's no phase shift, we start at time 0 and then go by steps. This is time 1, and then here's time 2. There you go. And the 100 doesn't really come into play because it's very difficult to deal with, this is the d-axis, to graph the 100. But this basically means at 0 seconds, the distance along the wall that light has moved. It assumes, by the way, the light is at 0 seconds pointing straight at the wall. So the distance is 0 at 0 seconds. And then as time goes on, that distance increases until about a second later, that light is beaming off to infinity, basically. And then, lo and behold, the other part of the light is coming around, and it's behind. It's a negative distance. It's this way, a negative distance, and it keeps creeping up until it's 0 distance again. And that's what that negative part right here is showcasing. So anyhow, that's a good, well, pretty much the only example with the tangent. And that's how it's done. This is actually used in calculus, to be honest with you. So it is good to kind of familiarize yourself with this function. It's going to be a while before you really use it in calculus, but it does occur in calculus.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.